Talking about cumulative distribution functions should be quick because we already have used them as we talked about normal distributions. But as we fill in some of the nooks and crannies about the concept of a cumulative distribution function, we'll remind ourselves of things like the fundamental theorem of calculus in its derivative form, as well as we're going to pick up some more statistical terminology. Let's take a look at cumulative distribution functions. Basically, one of the questions that in our context is how would you compute probabilities for a density function such as a standard normal distribution, and it can be proved that this thing does not have a nice antiderivative, and so the solution really is to make a numerical table, and this is not just limited to the standard normal distribution, even though it is a very important distribution in statistics. There are quite a few other distributions that have real applications and for which we just can't find a nice antiderivative. So these kinds of tables of cumulative distribution functions are therefore rather common in statistics. Alright, so the definition now is that the cumulative distribution function for a continuous random variable with probability density function lowercase f is defined by being capital F of x being the probability that the random variable gives you a value less than or equal to x, which is the integral from negative infinity to x of your density function f of y dy. And so that means that in the density picture, and I keep using pictures that look like normal distribution because that's what our main example is, but we're also going to see some animations for some other stuff. In the density picture, the probability that we get a value to the left of x is the area to the left of x, and so the area to the left of x is the value of the cumulative distribution function, whereas the area to the right of the value is 1 minus the value of the cumulative distribution function. And in the distribution picture, basically what we get is the distribution function aggregates the area up to a certain point, and so then the value of the distribution function at x gives you the area up to that point, and the difference between that value and 1, that is the area to the right of that point. In a static picture, that's about as much as I can do, I think. And in a moving picture, well, up top we have a density function, and in red we're aggregating area, and on the bottom we have what the cumulative distribution function does, and we can see that, well, as long as there's a lot of area to be aggregated, the cumulative distribution function rises rather quickly. If there is a region where there is very little area to pick up, the distribution function flattens out, and overall the distribution function just gives us the aggregate area up to that point. And we can also look at that in more concrete scenarios, such as the cumulative distribution function for the uniform distribution that we know. And of course, that's a bit of overkill, because to compute uniform probabilities, you just compute areas of rectangles. But then it should also not be a surprise that with a constant area of rate of picking up area, that the cumulative distribution function for the uniform distribution is in fact just a straight line, right? Then we can also look at the exponential distribution, and again we can compute these integrals directly, but we can see because the exponential distribution decays, that means that the cumulative distribution function of the exponential distribution rises quickly at first and then ultimately is asymptotic to 1, well, asymptotic to 1 like every distribution function actually will be. We will prove that. And finally, for the standard normal distribution, we get that we get a slow rise at first, then of course in the middle we get the fastest rise, and then at the end it flattens out as it goes towards 1. Okay, so this is the kind of thing that then also reminds us again of what the fundamental theorem of calculus in its derivative form does, which is these kinds of functions with a variable upper bound, they just aggregate areas, and cumulative distribution functions are a very important example of this process. Okay, so now let's take a look at a continuous random variable with cumulative distribution function f. And for all real numbers a and b, we then have the following: the probability that the random variable is greater than a is 1 minus f of a, and the probability that the random variable is between a and b is f of b minus f of a. That ought to make sense. Let's take a look at the pictures. First, probability that x is greater than a. Well, if a is here, then the probability that x is greater than a is here. That means that the probability that x is smaller than a is over here, and that probability, of course, is f of a. So this probability is complementary to f of a, so it's got to be 1 minus f of a. If we're looking at the probability to be between a and b, well, here's a, here's b. This probability is this area, which is the area to the left of b, which is f of b, minus the area to the left of a, which is f of a. So we've got the pictorial situation, and we can also do a symbolic proof. The probability that x is greater than a is the integral from a to infinity f of the density dx, which is 1 minus the integral from negative infinity to a of the density, and that's of course 1 minus f of a. And similarly, the probability that x is between a and b, that's the integral from a to b of the density, which is the integral from negative infinity to b of the density minus the integral from negative infinity to a of the density. And that's f of b minus f of a, and that finishes that proof. So we're in a situation here where we can also do some symbolic justifications. If we have a continuous random variable with cumulative distribution function capital F and probability density function lowercase f, then we actually have that the density function is the derivative of the cumulative distribution function. Okay, technically we also need to have that lowercase f is continuous, but let's just go through the argument here. If we take the derivative of the cumulative distribution function, then that is the derivative of the integral from negative infinity to infinity of the density, and we know that that is the derivative of, just to really actually fit the form of the fundamental theorem of calculus in its derivative form, that's the derivative of the integral from negative infinity to 0 of the density plus the integral from 0 to x of the density. And now this one here is a constant, so that derivative is 0. And by the fundamental theorem of calculus in its derivative form, we know that the derivative of an integral with a variable upper bound is just the integrand at that upper bound, so that is f of x. And yeah, so again, we're just recalling a few things that will come to us every so often. We're refreshing memory a little bit here. If we take a cumulative distribution function, then we will always have the following properties, namely cumulative distribution functions will be non-decreasing. For any real numbers, we will have that the value of the cumulative distribution function will be between 0 and 1. And we will have that the limit as the x goes to negative infinity of the cumulative distribution function is 0, and the limit as x goes to infinity is 1. And that comes from the following. For part 1, well, if a is smaller than b, right, that's what we have to talk about when we talk about stuff that is non-decreasing, well then, the value of the cumulative distribution function at a is the probability that x is smaller than a, which is less than or equal than the probability that x is smaller than a plus the probability that x is between a and b. And that's the probability that x is smaller than b, and that's the cumulative distribution function at b. So we have a smaller than b implies that fxa is smaller than or equal to fx of b, and that's what it means to be non-decreasing. For part 2, well, part 2 follows from the fact that probabilities are non-negative and never exceed 1, right? These numbers here are probabilities, and therefore they have to be between 0 and 1. Finally, if we're looking at the limit of the cumulative distribution function, that's quite a mouthful for me, so I'm trying to slow my pronunciation down, of fx of x, well, that is the probability that your outcome is not a real number, and basically we are measuring the probability that a process that returns real numbers returns a real number in a certain range. So the probability that this process doesn't return a real number is 0. Take a look at the limit as x goes to infinity of the cumulative distribution function. That's basically the probability that our random variable returns something between negative infinity and infinity, and that's 1. And that should already be the end of that proof, and it is. And well, now we take a look at some standard probabilistic language. If we have a number p between 0 and 1, then the 100th percentile of the distribution of the continuous random variable x is the number eta of p, so that the following happens, so that p is equal to f of eta of p is equal to the integral from negative infinity to eta of p of the density function. Okay, so what does that mean? Basically, eta of p is the cutoff, so that p probability for this process lies to the left of eta of p, and the median of a continuously distributed random variable is the 50th percentile, and that's denoted mu tilde often. And so basically the idea for these percentiles is the following. If we're looking at the density, we are interested in a probability p being to the left of the number, and that number then is just called eta of p, and so that would be the p percentile. So when on a standardized test you're in the hopefully 95th percentile or so, that'd be good for you, because that would mean that 95% of the distribution, 95% of the other test takers actually did not make it to your score, so that would mean you've gotten a really, really good score. In the distribution picture, it looks similar. Basically, we just have to remember that the distribution function is non-decreasing, and that means the probability, the cutoff p, is an output value, and the eta of p is an input value. And basically what it says is that, again, the percentile is just the value that is associated with the p as an input. So basically this mapping, this function eta, is essentially the inverse function of the density function here. So in spreadsheets, percentiles are computed with the inverse cumulative distribution functions, and that is because that's what the percentile is in mathematical terms, right? If a function undoes another function, then these two functions are inverses of each other. Okay, so for the standard normally distributed random variable, we've got this density function that we keep mentioning, 1 over root 2 pi e to the negative z squared over 2. And that cumulative distribution function is the integral of that thing, and that cannot be expressed in closed form. I've said that very often now, and basically that still means we're interested in these probabilities, however. And so the way we handle this cumulative standard normal distribution function is that we tabulate it. So this is something where somebody, especially in the day and age before computers, and people already did this kind of probability before then, somebody really sat down with an integration rule like Simpson's rule or so, and by hand computed all these values. The remainder of this presentation is now just all about how we get values out of the table. And before we do that, a quick word on spreadsheets and mathematical packages that provide these functions. For goodness sakes, use them. If you have your computer fired up and if everything is there and you don't want to use a table, it's probably as fast to just type things into the package. And so also, for example, the table that we've got on the previous panel, I made that with a spreadsheet. But make sure that the function you use really provides the values that you are looking for, because, well, programming is done by programmers, and there's nothing wrong with being a programmer, but sometimes the standard mathematical or statistical language isn't quite implemented in the help function, and one way to get over that is then to simply look at some values in a table and compute the corresponding values with the spreadsheet function to just make absolutely sure that you get the right values. Okay, so we now just look at a standard normally distributed random variable, and we're going to compute some probabilities. For example, the probability that z is less than 1.53. Well, basically you look at the table, and the way this table is set up is that the first two digits are on the vertical axis, and the second digit behind the decimal point is on the horizontal axis. So if I'm looking for 1.53, well, I've got 1.5 here, the 3 is here, and the probability is at the intersection of these columns, and so the probability is approximately 0.9370. We always want to say approximately here, because these values are all approximate values. There could be more digits computed, it's just that the table would get too large. Okay, well, duh, right? I mean, how hard could that be? Now we're just going to go through all the other kinds of computations. For example, if we're interested in the probability that z is greater than 0.78, well, 0.7 is here, the 8 is here, so the value is actually 0.7823, but it's the wrong one. It's the complementary probability. and so the probability that z is greater than 0.78 is 1 minus the probability that z is smaller than 0.78, and that's 1 minus 0.7823, and that's 0.2177. Just straightforward arithmetic. If we're interested in the probability that z is smaller than negative 1.1, well, the probability that z is smaller than negative 1.1 for normal distributions, if you're interested in the area to the left of a negative number, that's the same as the probability to be to the right of the corresponding positive number. So this is the probability of z greater than 1.1. And that's 1 minus the probability of z smaller than 1.1. And that is something we can compute with the table. Probability of z smaller than negative 1.1 is approximately 1 minus 0.8643. Okay, I didn't do the animation anymore because that's pretty primitive here anyway. And that turns out to be 0.1357. And what else can we do? We can find the probability that a number is, that the outcome is between two given numbers. Well, so the probability to be between negative 0.5 and 1.69 is the probability to be to the left of 1.69 minus the probability to be to the left of negative 0.5, which is the probability of being to the left of 1.69 minus the minus 1 minus the probability to be to the left of 0.5. That typical transformation, right? You flip it over, probability of z greater than 0.5, and then 1 minus the probability of z smaller than 0.5, and now those numbers, after some cleaning up of negative signs, we can compute. And well, I didn't even bother to write down the numbers here. Let's see, 1.69 would give us 0.9545, right? I did. And then the probability of z smaller than 0.5 gives us 0.6915. And we have minus 1. And you do the algebra, you end up with 0.6460. Finally, let's look at the 80th percentile for a standard normally distributed random variable. So now we're looking at a cutoff for this area being 0.8. The highlighting is just not that good at times. And so this is the x that we're looking for. Well, the eta of 80%, that would be eta of 0.8. Well, now we have to look at the numbers themselves. 80% is 0.8. Well, 8.8023 is here. 0.7995 is here. And so 0.84 ought to be the 80th percentile. That's approximately that. And so it's approximately 0.84. Now notice here that actually neither of the two values, this one or that one, hits 0.8 exactly. In days gone by, students would learn how to do linear interpolation in these tables to get slightly more accurate answers, but with computers now available, you can get as many digits as you want out of a spreadsheet by just using the right functions. And so if more digits are necessary, for goodness sakes, use a computer. The interesting thing is, and I'm not sure if that's because statisticians are conservative or because I've missed something, tables are still quite frequently in use, and that's simply because as you're working with a book, you've got one entity in your hand, and then it is a lot simpler to just flip to the back and look up values than to start working with another device. I'm not sure if that's going to change with the emergence of electronic books and the like, but I'm seeing people using statistical tables for quite a while, simply because looking things up sometimes is also just easier than to figure out how to do this on a spreadsheet if you've never done it before. Alright, with that, assignments can't be that hard, right? I mean, just look up values in tables and use things in spreadsheets. Get yourself used to working with cumulative distribution functions. Think a little bit about the properties of these functions, because that's a pretty nice exposure to the derivative form of the fundamental theorem of calculus. And with that, well, you get to it.